Hello students, today we are going to discuss ray optics and optical instrument NCERT section 9.2.3 and example 9.1 and 9.2. This is a disclaimer. So after this lecture you will be able to understand the principles of image formation and ray tracing in spherical mirrors using geometric optics, apply mirror equation and magnification formula to analyze image characteristics and solve problems involving spherical mirrors. So index of topics that we are going to discuss today is 9.2.3 NCERT section, the mirror equation, that we are going to derive the expression for mirror equation. Example 9.1, example 9.2. So let's start with the mirror equation. So definition of image formation. Firstly, we will discuss about the image formation by concave mirror and convex mirror. Okay, both of them are spherical mirrors. So what is image? Image is formed when light rays from an object points actually converge to or appear to diverge from a point. Okay, so light rays coming from object after falling on the mirror, either it can be concave mirror, either it can be convex mirror. After reflecting from a mirror, the rays of light coming from object after reflecting from mirror, they converge at some point or appear to diverge from a point. Okay, they converge at a point in the case of real image, or they appear to diverge from a point in the case of virtual image. Okay, virtual image is formed behind the mirror. So so that image is virtual, and the rays, reflected rays, are appear to be diverge from that point. And in real image, the reflected rays actually converge and meet at that point and form real image. Okay. So real images can be projected on a screen because reflected rays actually meet at one point to form a real image. So real images can be projected on a screen. If we place a screen in the front of the mirror and we set the position of the screen from the pole of the mirror equal to the calculated distance of image, so the real image can be projected on a screen as rays physically meet, as rays actually meet at that point of real image. Virtual images cannot be projected as virtual images are formed behind the mirror. Like in the plane mirror, you see daily, that is plane mirror, that is a part of spherical mirror also. So large spherical mirror is taken and small part from that spherical mirror is taken. So if a spherical mirror of large radius of curvature is taken and small part from that spherical mirror is taken, it will be nearly straight or plane. So that's how plane mirror is formed. Okay, so plane mirror forms virtual image that is formed behind the mirror. So the image that we see in the mirror of ourselves, that is virtual image. So that image cannot be projected on the screen because that is formed behind the mirror. Only real images can be projected on the screen. So image formation establishes a point-to-point correspondence between the object and image. We can take any two rays emanating, means emerging or starting from a point on an object. Okay, so there is an object placed in front of the mirror. So we can take any two rays. To form an image, we have to consider any two rays that is emerging or starting from any point on the object. Okay, we need at least two rays. Okay, but at most a number of rays can be taken, but at least we only need two rays that is starting from any point on the object. Then we have to trace their path and find their position of intersection after reflecting from the mirror. Okay, does the point of intersection after reflecting from the mirror can be taken as image due to the reflection at the spherical mirror. Okay. Ray tracing rules for spherical mirrors. So there are some rules that from which rays are passing, and after reflecting where ray will go, refracted ray will go. So there are some rules for ray tracing. Okay, that in figure 9.5 also it is being shown ray diagram for image formation by a concave and convex mirror. Now you can see in the concave mirror left side of the diagram, the ray that is going parallel to the principal axis, after reflection it is passing through focus. That is the rule for ray tracing. Okay, now you can see in the case of convex mirror, the ray that is going parallel to the mirror appears to come from the focus. You can see there is a focus. So this ray after reflection, it appears to be come from focus. Okay, now second, a ray that is falling on a pole, it is reflected according to the law of reflection. Similarly, in the convex mirror, a ray that is falling on the pole is reflected according to the laws of reflection, that is I is equal to R. Incidence angle is equal to angle of reflection. Now, the ray that is passing through this C, center of curvature, retraces its path. So it will directly reverse its path. So it is coming through C and falling on the mirror and exactly returning on the same path, retracing its path. Similarly, for that convex mirror, you can see a ray that is coming towards C, directly retraces its path. Okay, and the second one, okay, these are the 3 ray tracing rules for spherical mirrors. Okay, and if any ray is passing through focus, it will become parallel after reflection, or any ray that is coming exactly towards focus will become parallel after reflection. Okay, so these are some rules. Now you can see why the ray that is passing through that center of curvature exactly retraces its path. Why? Because we know that if we draw normal at any point on this mirror, that normal will pass through the center of curvature. Okay, so a ray of light that is coming along the normal, that is falling perpendicular at any point, the angle of incidence will be 0. So angle of reflection will also be 0 degree. That means it is coming through a path, and after falling, it is falling normally because it is passing through center of curvature. Normal also passes through center of curvature at any point. So it is coming at angle of incidence 0. So it will retrace its path at angle of reflection 0. So it will retrace its path exactly. Okay, that's why ray passing through center of curvature or ray coming directly towards center of curvature in the case of convex mirror retraces its path. So standard rays for construction of ray diagrams. So to find the where image is formed, we took only at least 2 rays. So 2 rays are taken based on these standard rays. Okay, so these are standard rays. The ray coming parallel, the ray falling on the pole, the ray passing through center of curvature, or ray passing through the focus. That are standard rays that can be used for the image formation in the ray diagram. So ray parallel to the principal axis, that one in both cases, reflects through the focus in case of concave mirror, or appears to reflect from the focus in case of convex mirror. Okay, ray passing through or appearing to pass through the center of curvature. So ray passing through center of curvature in the case of concave mirror, ray appears to pass through the center of curvature in the case of convex mirror. So reflects back along the same path. It will retrace its path. Okay, now other 2 rays, ray passing through or towards focus, ray passing through focus or ray coming towards focus, reflects parallel to the principal axis. So if ray is coming parallel, it will pass through focus. If ray is passing through focus, it will become parallel. So these 2 rules are interchangeable. or vice versa to each other. Ray striking the pole. So ray that is striking the pole in both cases follows regular law of reflection. Means angle of incidence will be equal to angle of reflection. Got it? These standard rays or ray tracing rules for spherical mirrors. So derivation of mirror equation. So ray diagrams for image formation by a concave mirror. So figure 9.5, that figure shows the ray diagram considering 3 rays. So we are considering 3 rays. Which ray? One is parallel to the principal axis, one is striking on the pole, one is passing to the center of curvature. And after reflection, all these rays meet at one point. Okay, so this is AB object, and we have considered the top point of this object. Okay, so image will be formed. So this A point, this part of the object will be formed as image where reflected rays will intersect. So we are taking one parallel ray. It is after reflection, it is passing through focus. We are considering one ray striking at the pole. So according to the laws of reflection, it will pass through, it will intersect that ray, that reflected ray at some point. And we are considering another, we only need 2 rays, but we are considering third ray also for checking the accuracy. So one that ray is passing through center of curvature, it will retrace its path. So it is also intersecting at the same point. That point is the reflection of that A point, that is A dash. Since this object is placed perpendicular to the principal axis, so we can draw the perpendicular line on the principal axis from here. So it will become A dash B dash, that is the image of this object AB. That image is inverted in this case. Okay, and it is smaller in size as compared to object. Got it? So figure 9.5 shows the ray diagram considering the 3 rays. It shows the image A dash B dash, in this case real. So this is a real image. Okay, image formed on the same side of the object, and inverted image is real image of an object AB formed by the concave mirror. Okay, so why this image is small sized? Because object is placed beyond C. We will discuss different cases where object will be placed and what nature of image will be formed. Okay, so this AB object is placed beyond C. So image is formed between focus and center of curvature. If this object is placed at infinity, then image will be formed at focus. If this object is placed at C, image will be formed at C. If this object is placed at between focus and center of curvature, then image will be formed beyond C. Means if we are bringing this object near the mirror, the image will go farther away from the mirror. Okay, when we place this object at focus, image will be formed at infinity. You can see when object was at infinity, image formed at focus. When object at focus, image formed at infinity. When we place this object between pole and focus, then the image formed is virtual. Only one case of concave mirror forms virtual image. Other 5 cases form real image. Okay. Now, it does not mean that only 3 rays emerge from the point A. So we are taking only 3 rays, but it doesn't mean that only 3 rays are emerging from point A. Number of, okay, we cannot count. The number of rays are emerging from point A, but we cannot consider all the rays. So we are considering only 3, or at least we can consider 2 rays. So 2 rays are needed, at least 2 rays are needed to form an image. So an infinite number of rays emerge from any source in all the directions. We now derive the mirror equation or the relation between the object distance. Now we will derive the mirror equation, that is the relation between object distance u, image distance v, and focal length f. So from figure 9.5, the two right angled triangles. So what triangles? Right angle triangles A dash B dash F. So this A dash B dash F, this small triangle, and MPF, this MPF. Okay, since this M and since the rays we are considering are paraxial. What are paraxial rays? That are very close to the principal axis. So these rays are very close to principal axis. Okay, so M and P, this line can be considered straight. Instead of curved line, it can be considered straight because this ray is very close to principal axis. That's why we are considering this as straight line and MPF as a triangle. So they are similar triangles. What are similar triangles? You may have studied in 10th class. Similar triangles. Okay, one chapter is for congruent, checking for congruency. One is for checking similarity. So what is similarity? Okay, one large ball and one small ball. Okay, they are similar to each other, but their size is different. Okay, two triangles are given. They are similar, but their size is, one is large sized, one is small size. So something similar that differs in size, but according to their structure, according to their configuration, they are similar. Okay, so these two triangles are similar. Why? Because 90-degree angle, this MPF, this angle P is 90-degree because we are considering this MP as straight line. So this is 90-degree angle. Also, this angle is vertically opposite angle. These are also equal. Okay, and if two angles are equal of any triangle, third angle is also equal. Okay, so this is common angle, this is 90-degree angle, so third angle will be same also. So AAA, from this, these two triangles are similar. Okay, so for paraxial rays, MP can be considered to be straight, this line perpendicular to CP. Also triangles A dash B dash P and ABP are similar. Also these triangles A dash B dash P and ABP, these are similar. Why? Because this is 90-degree angle, this is 90-degree angle. Also this angle A dash B dash P, this angle of reflection, and ABP, in triangle ABP, this angle of incidence, they are equal according to law of reflection. If two angles are equal, then third angle will also be equal. So according to AAA similarity, these two triangles are similar also. So from similarity of triangles A dash B dash F and MPF, these two triangles. So B dash A dash. So when two triangles are similar, we can take the ratio of their corresponding sides. Okay, ratio of their corresponding side will be equal. Means if they are similar, so B dash A dash, okay, or another triangle MPF, which side is corresponding to that A dash B dash similar to? So this is perpendicular line and having angle this. So MP is corresponding to that A dash B dash in triangle A dash B dash F, and MPF, these two lines, these two sides A dash B dash and MP are corresponding. So we can take their ratio B dash A dash upon PM. So ratio of their sides will be equal to the other two corresponding sides of the two different triangles, two similar triangles. So B dash F, which line is corresponding, which side is corresponding to that side of other triangle? That FP. Okay, so B dash F upon FP. So sides, so ratio of their corresponding sides of two triangles can be taken. So B dash A dash upon PM equal to B dash F upon FP. Okay, since PM is equal to AB, you can see this is parallel line. So AB is equal to this PM. PM is this MP or PM is taken as straight line. Okay, so AB is equal to this MP or PM. So we can take PM equal to AB. So in place of PM, we can write BA. So B dash A dash upon BA equal to B dash F upon FP. Mark it as 9.4 equation. From similarity of triangles A dash B dash P. Now other two triangles A dash B dash P and ABP. What are their corresponding sides? We can take the ratio. So A dash B dash, side corresponding to that side of the another triangle. So AB of ABP is corresponding to that A dash B dash of the A dash B dash P triangle. Okay, so these two sides are corresponding sides in similar triangles. So AB and A dash B dash. So we can take the ratio B dash A dash upon BA equal to, so other two corresponding sides, so B dash A is corresponding to, so what are corresponding sides that the two triangles are similar? So if we place them in the same orientation, so which side corresponds to other side of the triangle? Okay, if we are placing, you can see two right angle triangles are there. So we are, one is large in size, one is small in size, but they have same structure. So it base of one triangle will correspond to another triangle. Perpendicular of one triangle will be corresponding to other triangle and hypotenuse will correspond to other. Similarly, for similar triangles, there are corresponding sides based on their structure. So A dash B dash is corresponding to AB. So B dash A dash upon BA equal to B dash P upon BP. So this is the ratio of their corresponding sides. Okay, this you have studied in maths in class 10th. So this is the concept of class 10th. So mark it as 9.5 equation. So we have found B dash A dash upon BA equal to something else in the 9.4 equation. So equating equation 9.4 and 9.5, we came to a conclusion that B dash F by FP is equal to B dash P upon BP. So what is this intermediate term? So BF B dash F can be written as B dash P minus FP. So it can be written as B dash F can be written as B dash P minus FP. Okay, so this term B dash F upon FP equal to B dash P minus FP upon FP, which is equal to B dash P upon BP by equating 9.4 and 9.5 equation. So we came to another equation 9.6. Now we will put the values and find the relation. So relation between object distance U, image distance V and focal length F. So applying sign conventions, all distances are measured from the pole. Okay, so we will measure all the distances for pole. Light travels from object. So light is traveling, incident light is from object to the mirror. So direction of incident light is from left to right. We are measuring every distance, image, object and focal length, focus, all are in front of the mirror. So we are measuring from pole. So we are going in the direction opposite to the incident light. So all distances will be taken as negative if we are moving against the direction of incident light. So light travels from object to mirror, that can be taken as positive direction. So B dash P, this image distance. So we are measuring from pole, we are moving against the direction of incident light. So B dash P will be taken as minus V, which is image distance. Image distance is V and we are taking negative sign because we are measuring it against the direction of incident light. Also FP, focal length. We also know that focal length of concave mirror is always negative. So minus F because we are measuring from pole to focus. BP, we are measuring from P towards B. So object distance is also taken as negative. So if object is real, means it is in front of the mirror, so it will also be taken as, always be taken as in negative sign. And focal length of concave mirror is negative and image is formed in front of the mirror, so it is also negative. Now put b dash p equal to minus v, fp equal to minus f, and bp equal to minus u in 9.6 equation. So substituting all the values with sign conventions in equation 9.6, which is b dash p minus fp upon fp equal to b dash p upon bp. So now put all the values we have calculated. So b dash p is minus v minus fp. Fp is minus f. So minus minus f becomes plus f, and fp is again minus f. B dash p is minus v, bp is minus u. Okay, so after putting all this value, now solve it to find a final expression. So relation between object distance u, image distance v, and focal length f. Simplifying. Now after simplifying it, negative and negative sign will get cancelled out, and this negative in the denominator will go in the numerator. It will become v minus f upon f equal to v upon u. Now multiply f on the right hand side. So v minus f equal to vf upon u. Now dividing by v. So divide this equation with v. It will become v upon v, f upon v, and vf upon uv. So v upon v will become 1 minus f upon v equal to this v and v in the denominator will get cancelled out, f upon u. So after dividing it with v, it will become 1 minus f upon v equal to f upon u. Got it? So after arranging this equation, you will get the final equation. So 1 minus f upon v equal to f upon u. So now finally dividing it with f. So it will become 1 upon f, and f upon vf will become 1 by v equal to f upon u, f will become 1 by u. So 1 by f minus 1 by v equal to 1 by u. Now rearranging it the last time. So it will become 1 by v plus 1 by u equal to 1 by f. Mark it as 9.7 equation, and this is the famous mirror equation. So all the mirror problems, all the we have to find the image distance, or image distance is given, we have to find the object distance, or both image distance and object distance is given, we have to find the focus or focal length. Okay, for convex or concave, any type of mirror. So this is a universal mirror equation applicable to all type of mirrors, all type of spherical mirrors and plane mirror also. Okay, so this is the mirror equation. So you have to put the values in numericals, values will be given. Okay, but you have to remember or consider the sign conventions. Okay, if you are not considering the sign conventions, then you will get wrong answer. You have to consider all the sign conventions and put the value in this equation, you will get the answer. So this is universal mirror equation applicable to all optical systems and all type of spherical mirrors. So now we'll discuss what is linear magnification. So linear magnification is a ratio of image distance, image height to the object height. Okay, so what is magnification? What is its physical significance? That means how much image is magnified. The image formed is as compared to the size of image as compared to object. Okay, so it is the ratio of image height to the object height. It is having no unit because we are taking ratio of height to height. So it will give only the measure that how much times, how much amount of means about what amount of image height is greater or smaller than object height. So m is equal to, linear magnification is represented by small m, which is equal to h dash upon h. H dash is the image height, h is the object height. Mark it as 9.8 equation. Now magnification in the terms of image distance v and object distance u. Okay. So from similarity of triangles a dash, b dash, p and abp. Now again, similarity of triangles a dash, b dash, p and ABP. We can write B dash A dash upon BA, that we have written in 9.5 equation, equal to B dash P upon BP. Okay, this thing we have marked as 9.5 equation earlier. So applying sign convention to this equation, you will get minus, so B dash A dash, it is height of the image. According to sign conventions, it is formed below the principal axis. So height of this image will be taken as negative. So minus H dash upon height of this object. Object is above the principal axis. So it will be taken as H, which is equal to B dash P. So B dash P is distance of the image from the pole. Okay, since we are measuring every distance from pole, so according to sign convention, it will be taken as minus V. And object is also in front of the mirror, it is taken as minus U. So BP is object distance, minus U. Now after rearranging, you will find the relation H dash upon H. So therefore magnification is equal to H dash upon H, which is equal to minus V upon U. So this is the final expression, 9.9 equation. So magnification can be represented in the form of ratio of heights of image and object, and also in the terms of image distance and object distance. Okay, so this is the expression for linear magnification. So significance of linear magnification. So positive magnification. So positive magnification means image is formed on the same side of object. Okay, if object is above the principal axis, then image is formed above the principal axis. That means magnification is positive. If object is below the principal axis and image also formed below the principal axis, then again magnification is positive. But if object is above the principal axis and image is formed is inverted, that means magnification is negative, and that inverted image is real. But image on the same side of object, I am considering with respect to principal axis. Means if object is above the principal axis and image is also above the principal axis, that means image is virtual and erect, and that image will be formed behind the mirror, not in front of the mirror. And negative magnification means image is inverted, and inverted image means image is real. If it is formed in front of the mirror, it is inverted, that means it is real. Now magnitude of magnification M. If it is greater than 1, that means image is magnified. Okay, it is the ratio of image height to object height. If it is greater than 1, that means image is magnified. Size of image is more than the object. And magnitude of magnification is less than 1, means without considering the sign. So its magnitude is less than 1, it means image formed is smaller in size, or we can say diminished image. Diminished means smaller in size as compared to object height. Got it? And if magnitude of M is 1, that means same sized image. Object height and image height is same, due to which magnification is 1. Okay, that is the physical significance of magnification. Now, nature of the image formed by the spherical mirror. So these are figure 9.6, image formation by concave mirror with object between P and F, and B is a convex mirror. Now you can see the case of virtual images shown for concave mirror. When image is placed between focus and pole, when object is placed between pole and focus, then the image formed is virtual. This according to this ray diagram. Okay, you can see. So the reflected rays are diverging rays. So after extending them behind the mirror, they will meet at a point and forming virtual image behind the mirror. So only one case of concave mirror is for virtual image. Other 5 cases are for real image. In convex mirror, it is not possible to form real image. Only virtual image is formed. And there are only 2 cases. When object is placed beyond focus and when object is placed at focus. Only 2 cases are there. When it is placed at infinity, image will be formed at focus. When it is placed between infinity and pole, image will be formed between pole and focus. And image will also be diminished. We cannot form the magnified image in convex mirror, but we can form magnified image or magnified virtual image in the concave mirror. Okay, the mirror that is used by dentists, okay, they insert a mirror to see your magnified image of your teeth, to examine your teeth. That mirror is used as concave mirror. They place your teeth within the focal length of concave mirror. Okay, so concave mirror will form a virtual image when object is placed between focus and pole or within its focal length. It forms a magnified virtual image. So the mirror used by dentists is magnified. That is, mirror is used concave mirror. Also, concave mirror is used in solar cookers. Okay, it converges the light rays coming from sun, a very distant source, are parallel. So that is parallel beam of light. After reflecting from the concave mirror, it will converge at one point at focus. Okay, so concave mirrors are used in solar cookers also. Also in the headlights of car or bike. Okay, so that bulb that is placed in your, you can see that in headlight there is a background, that is reflecting background, which is curved, somewhat curved. It is not straight. So it is formed in the form of concave mirror. Okay, and bulb is placed at the focus of that concave mirror. When bulb glows, ray of light coming from that bulb will strike the concave mirror behind it. Since the bulb is at focus, so light rays coming from focus, so object is at focus. So after reflecting from the concave mirror, they becomes parallel. So parallel beam of light is formed in the headlights due to concave mirror. Okay, and convex mirror, application of convex mirror. So convex mirror is used in side view cameras. Side view mirrors in the vehicles. Okay, the side mirrors that you are seeing in your bike or in car. Which mirror is used? Convex mirror. Okay, it form diminished image and it covers the large view. You can see the vehicles that are behind you are visible to you, but they are visible in small size. They seems to be smaller in size, and large field view is taken. So that's why convex mirror is used in the side view mirrors. Okay, so these are some applications. So universal nature of mirror equation, what is it? Equation 9.7 and 9.9 are valid for all spherical mirrors. So that equation for magnification and mirror equation that are valid for all spherical mirrors work for both concave and convex mirrors. Handle both real and virtual image. That equations are applicable everywhere to find when images formed are real and virtual, when a mirror used is concave or convex, or for all spherical mirrors. Okay, so applicable for all object positions. Means they are universally applicable. Figure 9.6 shows the ray diagram for virtual image formation by the concave and convex mirror. You should verify the equation 9.7 and 9.9 are valid for these cases as well. Okay, so for any cases of virtual image, cases of real image, these mirror equation and magnification equation, that is valid. Okay, but you have to take into account the sign conventions. Okay, concave mirrors are used in solar cookers, headlights, or the mirror used by dentists to examine your teeth, okay, and in street lights. So there are many applications of concave mirror and convex mirror, okay. So image formation by a concave mirror for different positions of object. So there is a table that is describing that where what is the position of a object and corresponding to what is the position of image. So when object is at infinity, position of image is at focus, and size of the image is highly diminished, means point sized, and image formed is real and inverted. When we place the object beyond C but not at infinity, it is at finite distance but beyond C, then position of the image is between focus and center of curvature, and image is diminished, means smaller in size, and nature of image is real and inverted. When we place the object at C, then position of the image is also at C, and size is same, means magnification is 1, but nature of image is real and inverted again. When we place object between C and F, this is for concave mirror, so 6 cases are there. So between C and F, then position of image is beyond C, and size of image is enlarged, okay. Real and inverted image is formed. When we position of object is at focus, then image is formed at infinity, and image would not be formed, it can be said, means image will be formed at infinity, but we don't know where infinity is, okay. So image would not be formed, we can say, but nature of the image will be same, real and inverted. But only one case, when we place the object between P and F, pole and focus, then position of the image will be behind the mirror, and size of the image will be enlarged, and image formed will be virtual and erect. This application is used in the dentist mirror, that they are used to examine your teeth, okay. They place your teeth within the focal length of the concave mirror, then the image formed will be virtual and erect and enlarged image. So now nature, position and relative size of image formed by the convex mirror. So for convex mirror, there are only 2 cases: when position of the object at infinity, position of the image at the focus, okay, and behind the mirror. Size of the image is highly diminished, point sized, and virtual and erect image will be formed. And when position of the object is between infinity and the pole of the mirror, then position of the image will be between pole and focus, always behind the mirror, and size of the image will be diminished, and nature will be virtual and erect. So example 9.1, suppose that the lower half of the concave mirror's reflecting surface is covered with an opaque non-reflecting material. So half of the mirror is covered with non-reflecting material. What effects will have on this image of an object placed in front of the mirror? Okay, will image will be halved or anything else? So let's see, this example illustrates an important principle about image formation. So every point on the object sends light rays in all the directions, and only a fraction of these rays are needed to form a complete image. Okay, not all rays are needed to form a image. Okay, only a fraction of these rays that are emerging from the object, only a fraction of rays are needed to form a complete image. Okay, what are other rays doing? They are making the image sharp. Okay, number of rays reflecting or forming an image represents its sharpness, that how sharp is the image. So what is the physical understanding for this question? When we cover half of the mirror, we reduce the number of rays that can reflect from the mirror. Okay, initially that rays coming from the object are reflecting from all parts of the mirror. Now it is reflecting from the half part of the mirror only. So we have reduced the number of rays. However, the remaining uncovered portion of the mirror still receives ray from the every point of the object. So half of the mirror is still making the image or taking the rays from the object. Okay. Each point on the object continues to have rays reaching every point on the uncovered mirror surface. So the part that is uncovered is taking rays from every point of the object. So each point of the object continues to have rays reaching every point on the uncovered mirror surface. That means image will not be halved. Okay, so effect on the image formation. What is the effect? the complete image will still be formed, because rays from each point still reach the uncovered mirror. Okay, uncovered mirror is accepting all rays coming from the, means number of rays coming from the object, and it is forming the image. The image position, size and orientation remains unchanged. Image will be formed at same distance as earlier, size of the image will be same, and orientation will also be same as initial case. The mirror equation and magnification formulas remain valid for half of the mirror also. So effect on the image intensity. So when we cover the lens or any mirror, so that affects the intensity of the image, the sharpness of image. Okay, so since half of the mirror area is reflecting light, so other half is not reflecting light, so number of rays that are reflecting and forming an image is reduced, due to which brightness or intensity of the image is reduced. Okay, approximately half the light that would normally form the image is lost. So half of the light is lost. Initially all the rays falling on the mirror are reflecting. Now we have covered the half mirror. Now half of the rays are lost, due to which image formed is of less intensity. So image appears dimmer but retains all its geometrical properties. But geometrical properties, that is position, size and orientation, will not change, but it will become dim. Okay, next example. A mobile phone lies along the principal axis of a concave mirror as shown in the figure 9.7, shown by suitable diagram, that is figure 9.7. The formation of its image. Explain why the magnification is not uniform. Will the distortion of image depends on the location of the phone with respect to mirror? Okay, why magnification is not uniform? The part, this is similar to the object, but this part is not similar to the object. So why magnification is not uniform? You have to answer that. So let's see why. So ray diagram analysis we will do. So part of the phone which is at C. So we know that when object is placed at C, the image formed will be of same size. Okay, of a concave mirror. So when part of the phone which is at C will be imaged at C, that part that is placed at C will be imaged at C only. Image will be formed at C only and will be of the same size. That is U equal to R, V equal to R. So magnification will be -1. Why -1? Because image formed is inverted. That means BC is equal to B dash C. This distance will be same because this BC is placed at center of curvature. Okay, so that's why the image formed of this portion will be of same size. So B dash C will be equal to BC. Part of the phone which is farther from the mirror. Okay, point B. This part that is farther from the mirror will have its image B dash formed closer to the mirror. So it is at C, this BC part or this B part just above the C, center of curvature. So part of the phone in the object that is farther from the mirror, the image that B dash part will be closer to the mirror as compared to other part. So part of the phone closer to the mirror. So which part is closer to the mirror? A part. This A part is closer to the mirror. So image A dash will be formed farther from the mirror as compared to this B dash. Okay, why? Because this A is placed between F and C. Image will be formed for this A, image will be formed beyond C according to image formation cases of concave mirror. Since U is placed between F and R, then V will be greater than R. So it is placed between focus and center of curvature. So image will be formed beyond the C, center of curvature. Magnification will be greater than 1. Means image formed will be enlarged. So magnification is M equal to minus V by U, which depends on both U and V. Okay. So magnification depends on object distance. Since this A is closer to the mirror and it is placed between C and F, and this B is on C. So magnification depends on the U and V. That's why, since different parts of the phone are at different positions, So A part is between focus and center of curvature, B part is at center of curvature. So different parts of the phone at different object distances. That's why magnification is not uniform. Distortion of the image depends on the location. If the phone is placed very far, if this phone is placed very far away from, means the distance of the phone is very large as compared to the size of the phone. So phone is placed very far away, the magnification will be nearly uniform then. Okay, because this size of the phone is very less as compared to the distance of this phone from the mirror. So magnification will be nearly uniform, that all points, then this phone will be considered as a point object. So all points will be magnified, that magnification is nearly equal to minus f by u. Okay. So let's look upon summary. An image is formed when light converge or appear to diverge from a point. Real images can be projected on screen while virtual images cannot. 4 standard rays are used for ray tracing: parallel, through center, through focus, and through pole. The mirror equation is derived using similar triangles: 1 by v plus 1 by u equal to 1 by f. This is mirror equation. Sign conventions: light travel direction is positive. Image object distances and focal length follow signs. Magnification m is the ratio of image height to the object height. M equal to h dash upon h equal to minus v upon u. Positive m indicates virtual erect image. Negative m indicates the real inverted image. Magnitude of magnification greater than 1 means magnified image. M mod m less than 1 means diminished image. And m equal to 1 means same sized image. The mirror equation and magnification formula works universally for all spherical mirrors. Both mirror equation and magnification formula apply to concave and convex mirrors, real and virtual images, and all object positions. So there are some practice questions. A concave mirror has a focal length of 15 cm. If an object is placed 30 cm from the mirror, where will the image form? For a convex mirror with focal length 20 cm, find the magnification when an object is placed 10 cm from the mirror. Third question: an image is formed at 40 cm from a concave mirror when the object is placed at 20 cm. What is the focal length of the mirror? If the magnification produced by mirror is plus 0.5, is the image real or virtual? Or an object 2 cm tall produces a 6 cm tall inverted image. What is the magnification and what type of image is it? So use of mod in the magnification is for magnitude of, means we are not considering sign. We are only considering magnitude to find that image is diminished or enlarged. Okay, it is only to find the size of the image as compared to object by neglecting the sign. So thank you. This is all about today's lecture.